Hi again. If you followed the last video, you noticed that by applying lubrication approximation, we finally managed to find a solution for this problem, which connects the velocity of the plate as it's sinking down inside into this viscous oil and the force required for that motion to occur. F, namely Vp and F. We found the relationship between them, and we showed that indeed as the dividing gap or height h becomes smaller and smaller, the velocity of the plate sinking down becomes dramatically small because it goes as h cubed, and also it's inversely proportional with viscosity. So the higher is viscosity, the slower will be this motion. Now this is after few relatively elaborate steps of algebra. Sometimes as an engineer you may like to get this result without doing these steps of algebra, and sometimes you may have done these steps, you just want to check whether your final result makes sense or not. I'm going to show you a method that will give you the same kind of result, maybe not with the exact numerical prefactor, but with the exact right proportionality and formula that you can actually get with just simple scaling arguments. And the place that we start our work is simply this expression here. So what we have here is dp over dr, and which is the viscous scale for pressure gradient, and viscous stresses mu d2 vr over dz2 being equal to 0. So if we take the consequence of this, so let me rewrite it here. So 0 is approximately equal to negative dp dr plus mu d2 vr dz squared. The scaling consequence of this is simply the fact that the characteristic pressure divided by r, Pc over r, that's the scale of the first term, should scale as mu. Scale for velocity vr, scale for the velocity vr, we decided to call that u, mu u divided by h squared. And if you remember from continuity, we noticed that this u is actually connected to velocity of the plate, and you can actually come back here and show that, again, just using a scaling, u divided by r, u divided by the long scale r, should be a vp, which is velocity in the y direction, divided by the scale in the y direction, which is vp divided by h. So if we use this simple scaling, we can actually plug it there and find something simple that tells us Pc, the characteristic pressure, scales as mu Vp over h. So we just replace u with Vp. Mu Vp over h, and there is an extra r over h factor that comes with an extra h. It gives us times r over h squared. So that's the scale that we find for pressure. We didn't solve anything. We just look at the nature of the governing equation and the conservation of mass in terms of the scaling argument. And it tells us that the characteristic pressure should actually be viscosity times Vp over h multiplied to a geometrical factor r over h squared. So that's the scaling for the characteristic pressure you have beneath this falling disk. If we have that, then we can easily find the scale for force, because if you think about the force, and that's with magenta force, that scales as the characteristic pressure multiplied to area, so that goes as Pc multiplied to r squared. And if I do that, that simply comes down to this conclusion that force in this problem, F, should scale as mu Vp over h multiplied to r over h squared multiplied to r squared. Now I have something that is actually very interesting, because I have a scale that tells us how f and mu are connected. If I rearrange terms here, I can find the scaling for Vp. Let's do that together. And if I do that, I can probably continue it somewhere down here. So I just put an arrow and I continue it here. If I continue that, I will get that actually Vp, which is equal to negative dH over dt, is a scaling as the force that we have, which is F multiplied to h cubed divided by mu multiplied to r cubed. So in simple words, without doing any time-taking algebra, just looking at the scale of terms involved and the governing equation that I have, I will find that Vp should be linear with F, should go as h cubed, inversely proportional with viscosity, and we should go as r to the power of negative 4, because r to the power of 4 is in the denominator. It's exactly the same type or the same form of equation we found after the algebra. The algebra gave us this 2 over 3 pi factor. That may be important in an engineering application, but without doing that in a much faster shortcut, you can actually find the right form of your solution. So if you are in the exam sometimes not sure your final solution has the right form in terms of dependency on h to the power of 3 or 4 or 5 or mu and r, you can easily do this kind of fast scaling arguments in these lubrication problems and reach to the final conclusion, to the final result in terms of the right form and compare it to the form that you have done with extra algebra. Now, one thing that is also very helpful, whenever you get a result, it's very helpful if you check the units. Let's check the units together. So if I have a force times h3 over r4 will be a force divided by r. A force divided by r would be nothing other than a pressure multiplied to r. So if I take a pressure multiplied to r, I can divide both sides over r, so I will have a mu over r here and a pressure on top. And if I bring the Vp to the denominator, I will get a shear rate multiplied to viscosity, that's a stress, and I get a pressure on top. So really this equation, in terms of units and dimensions, is homogeneous and everything is consistent. You have velocity on this side, you have a scale of velocity on the other side too. So things are consistent and you have got a relationship that not only dimensionally is correct, but also the scales involved in this equation, the power laws involved, are consistent with the overall governing equation and all the physical scaling arguments that you can use. This is a very powerful technique and trick that I really suggest you to apply to many different problems and homeworks and sample quizzes that we have posted for you on this subject in MIT edX website. It's a very good way to wrap up your solution and see whether things that you are getting, apart from numerical factors that may change due to mistakes in algebra or things like that, whether they have the right form or not. I hope you guys will do that on your own, and I hope this will help you to check your solutions.